same. They look the same, they perform the same job. But if we look closely, really closely, we can spot some differences. So for instance, if we take a sheet of office paper, even with the human eye, we can spot maybe some slight irregularities in the surface. But if we look under a microscope at that surface, the plane surface is anything but plane. Under a microscope, we see an enormous jumble of the fibres, the wood fibres that make up that surface. And the patterns that those fibres produce are totally random and totally unique.
So how does LSA make use of these random surface variations?
Well, we've got a demonstration system here, so let me show you. What we do is we place the item onto the scanner and we scan a small laser beam across it. Now that laser is very similar to the sort of laser used in supermarket barcode readers, for instance. But LSA looks much more deeply than a normal barcode scanner would. It's looking at the actual structure that makes up the paper and not just the ink that sits on the surface. The laser bounces off the random surface imperfections and the scanner records the scatter pattern. LSA doesn't take a photograph of the surface, although sometimes we show photographs to illustrate the process. It's more like the surface pattern leaves an imprint in the reflected laser light, something that in physics we call light speckle. The result is every bit as unique as the minuscule random patterns on the surface itself. The light speckle is used to create a sequence of numbers totally unique to this object, which the scanner can refer to in the future.
So it sounds a little bit like a fingerprint, but on a much smaller scale.
Yes, that's exactly right.
So let's put the system to the test. How about if I mark some pieces of paper which, to our naked eye, look identical?
Okay.
And see if the system can tell them apart.
Okay, well first of all we will register them on the system. So we'll take the first sheet, we'll allow the laser to scan over it, and we'll tell the database on the computer here to call this sheet of paper 1. Mm-hmm. We'll then do the same with the second sheet. Mm-hmm. And we'll call that sheet of paper 2. And then again with the third. And finally with the fourth. Okay, so those 4 sheets are registered on the database. Mm-hmm. Now let's see if it can tell them apart. Yep. So maybe if you'd like to pick one of them.
All right.
So you've chosen sheet number 2 there.
Yep.
What we'll do is we'll ask it to rescan it, to compare that against its database entries and see if it recognises it. You see immediately it's pinged up there, sheet of paper 2, it knows which one this is. Mm-hmm. Should we try some others perhaps?
Oh yes. Mm-hmm.
So that's sheet of paper 3. Immediately that says sheet of paper 3, it knows which one that is. We've got 2 left.
Yeah.
Thank you. Knows that's number 1, and then the last one.
Yeah.
It knows that's number 4. It can tell them all apart.
Mm. But how reliable is the system? What are the chances of, say, having a false positive reading?
Well, the chances of a false positive are literally astronomical. The number of sheets of paper you'd have to try before stumbling across the same fingerprint a second time is somewhere around 10 raised to the power of 100. That's actually more than there are atoms in the entire galaxy.
Ah, that would take some time.
It would.
Let's just test it though and try another random piece of paper that, again, to the naked eye looks identical to the others.
Okay, so it's never seen this one before. And it knows that it hasn't recognised it.
So there we have it. LSA uses the naturally occurring random structure found on the surface of all objects to create a unique recognition code. Once the system has scanned an object and logged its signature, it can verify its authenticity the next time it's presented for scanning and be able to rule out any other items that aren't a match. In the next section, we'll see how LSA stands up to rough everyday handling, making the system genuinely daily life-proof.